Hi everyone, so today we're going to be doing the chemistry diagnostic for the periodics tomorrow. Let's start. Whenever you see miscible liquids with close boiling points, immediately fractional distillation, don't think about it. Now, an aqueous solution of hydrochloric acid, lumps of calcium carbonate. Whenever you have an acid reacting with a carbonate, it's only gonna release two things: the carbon dioxide gas and water. And since carbon dioxide gas is getting released, bubbles are gonna form. So that's it for this question. Now let's move on. Okay, this is equilibrium. We've took it a million times. Reversible chemical reactions, rate of forward and rate of backward. So rate of forward will go down, rate of backward will go up, so they can meet at one point called the equilibrium. Reverse increases. Equilibrium, the rate of the forward reaction and reverse reaction are equal and the concentrations always constant. It's dynamic due to the opposing microscopic processes that take place simultaneously at the same rate with no macroscopic changes. This is how the thing should look like always. Okay, changing temperature. When you have temperature decreasing, it's gonna, if it's exo, it'll shift forward, and if it's endo, it'll shift backwards for when temperature decreases. So let's identify what this is. This has endo, so it's gonna shift backwards. And the concentration of SO3, since it's shifting towards it, will increase. Now, second example is telling us when temperature increases. With an increase of temperature, endo will go forward and exo will go backwards. Let's see what this is. This is an exothermic reaction. So again, it's gonna shift backwards. And CO2, which is on this side, it's moving away from it, so it's gonna decrease. Okay, here you just have to label crystallization. Always, you're gonna start with the heating until most solvent evaporates. Then you're gonna move it to an evaporating dish in a water bath. Then you're gonna heat it carefully until all solvent evaporates, and then you're gonna leave it to dry and give you crystals. Now let's move on. Okay, so we want the RF values. The least, look, when it wants the dye of least solubility and most affinity, it means the one that sticks to the paper the fastest. It's always gonna be the one closest to the solvent, the baseline, furthest from the solvent front. So in this case, it's C. Now, I didn't read this question and realized they want the RF value for component A when I was solving. I gave them the one for C, but they want for A. And how do you find RF value? You're gonna take distance of A from baseline, divide by distance from solvent front. So 10 divided 12, which is 0.83. Now, let's see. Yellow precipitate, iodide ion. White precipitate, it's always chloride ion. I don't know how to write the ion for chloride, so I'm just gonna chloride ion. Then it's Cl minus, I think. Creamy precipitate, creamy bromide. Br2 minus or plus? I forgot. I'm not gonna write these anyways. And no change, it's always fluoride ion. Okay. Copper nitrate. What did we say about copper? Copper loves the color blue. Anytime you see copper, it has something to do with the color blue. Okay, this is memorizing. Reddish brown, Fe3. Green precipitate, if it does not dissolve in anything, it's immediately Fe2+. Does not dissolve, خلاص, Fe2+. Blue precipitate, like I told you, copper loves the color blue, so it's definitely copper. White precipitate, now we have 3 different white precipitates. With sodium hydroxide and no precipitate with ammonia means it could be one thing, calcium. white precipitate with ammonia and does not redissolve in excess ammonia. So it gives you a white precipitate in ammonia, but it's not soluble, meaning it can only be Al3+, because Zn is soluble in excess ammonia. White precipitate with sodium hydroxide and redissolves in excess ammonia, then it is Zn2+. Green precipitate with sodium hydroxide and soluble, then it's Cr3+. So yeah, now let's move on. So yellow-green gas and bleaches. When you see the word bleaches, immediately chlorine. Colorless, odorless, lit, a glowing splint, oxygen. Pop sound, hydrogen. Pungent smell and moist litmus paper blue, it's ammonia. Colorless gas that turns lime water milky. Carbon dioxide, you must know this if you took bio last year. Decolorizes purple acidified aqueous potassium manganate. Could only be one thing, sulfur dioxide. Okay. This one, metal, so it's basic. CO2, C is a gas, so it's acidic. Cu, metal basic. N2O is our exception, it's neutral. CO, also an exception, which is neutral. ZNO, amphoteric. Al2O3, amphoteric. S is not a metal, so it's acidic. And Ca is a metal, so it's basic. Okay. Anything before 7 acid? Anything. Actually, no, that's acid, base, neutral. So, okay. A is before 7, so it's acidic. B is on 7, so it's neutral. C and D are both after 7, so they are basic. Okay. So here we want hydrogen ions from KOH 0.6. So we just do 10 power negative 14 over the number of moles, 0.06. You're gonna get this answer when you put it into your calculator. Okay. So this one, it's a bit different. Look, they told you it's 0.400, but H2A. H2A meaning you double this. So 0.400 times 2, you get 0.800. Now to find OH, you do 10 power negative 14 over 0.800. You get 1.25 times 10 power negative 14. Okay, that's it. Moving on. Adding catalyst. We know catalysts don't affect equilibrium. They just make it faster, and concentrations will always remain constant when adding a catalyst or an inert gas. And here's your example about the inert gas. Again, not affected, and it will remain constant. And that's the end for chemistry, and have a nice day.